Continuing our exploration of how to write a rate law expression. It's a little bit more of the same. Now we're going to talk about initial reactants Q and X turning into products. We've got 3 trials. Similar kinds of tasks. Number 1, or part A, determine the rate law for the reaction above. And as always, we start with the generic rate is equal to K times, in this case, Q to some power, which we have to figure out, times the concentration of X to some power that we have to figure out. All right, so let's do that from our data. Let's take a look first at, we'll keep Q constant, what's happening with X. So Q will be constant in trials 1 and trials 3. All right, so if Q is constant, what's happening with X? From trial 1 to trial 3, we see a doubling of X, right? So if we take X and we double it, what's going to be that effect, right? We see that's a doubling. What's the effect on the rate? From 1.5 times 10 to the negative 3 up to 1.2 times 10 to the negative 2. Now it's kind of hard to see this mentally. What you should do is take in your calculator, take the larger number, which is this number here, and divide it by the smaller number, which is this number here, right? And so the effect of doubling reactant X, you're going to discover that when you divide those two numbers, it's going to be an increase of 8 times. All right, so what do we have to do? What power do we have to raise 2 to in order to get an increase of the rate to be 8 times? Right, so you might see that that is going to be to the 3rd power. 2 times 2 times 2 is 8. So what we have here, this is a little different from the ones we saw earlier. The reactant X is going to be to the 3rd order. We have to raise it to the power of 3 in order to see the effect of changing the concentration of X on the rate of the overall reaction. Okay. All right, so now let's do, we have to take a look where X is constant. Let's see what happens with Q. So if we take a look, I'm going to erase this so we can see this better. If X is constant, we see that is trials 1 and trial 2, where X is constant. What's happening with Q? Well, from trial 1 to trial 2, that is a doubling. What effect does that have on the rate? Well, this might be easier to see. From 1.5 up to 3.0, both are 10 to the negative 3rd power. So what we can see here is that the increase on the rate will also be a doubling. So doubling the concentration of Q only doubles the reaction rate, and so the exponent we're going to need there is a 1. Okay, so Q is going to be 1st order. If we jump to part C and we figure out the overall reaction order, this is going to be 1 plus 3, so this is overall 4th order. So that part's pretty straightforward. Okay, so let's go jump back to part B, where we have to find the rate law constant. Okay, so the rate law constant, we need to rearrange this where K is going to be equal to the rate over Q times X to the 3rd power. All right, and so to find the rate constant K, we just pick a trial. Again, we're going to pick trial number 1, where we substitute in the numbers from trial 1. In trial 1, the rate was 1.5 times 10 to the negative 3 moles per liters per minute, I believe. Is that what it said up there? Moles per liters per minute. Yep. Okay, I'm going to put that back. Sorry for the scrolling. We're going to divide that by the initial concentration of Q, which was 0.12 moles per liter. That's to the 1st power. The initial concentration of X was 0.10 moles per liter cubed. Okay. So let's take a look and see what happens with our units. Moles will cancel, liters will cancel. All right, if we start reducing down some of these numbers, we're going to see 1.5 times 10 to the negative 3. That's 1 over minutes. I'm going to scroll down again. All right, and so now the math down here, 0.10 times 0.10 times 0.10 times 0.12, that number is going to give you 0.00012. The units down here will be moles cubed over liters cubed. All right, and when we finally reduce this down, we're going to have a rate constant K equal to 12.5, although I think there's an error in the significant figures here. Perhaps we need to go to 2 sig figs. So yeah, I'm thinking that's got to be 13, and our final unit is going to be liters cubed over moles cubed minutes, right? So right there, that is your rate law constant for that particular experiment, for that particular equation. All right, we have one more problem that I'm going to work through with you together. Let's take a look here. Here we're given a bit more complicated looking equation, but you know what? It doesn't matter what the coefficients are. You're just going to be dealing with your products. In this case, we're calling them A and B, and we're measuring the initial rate of formation of one of the products. That's how this particular equation was being measured. Okay, so what we need to do, what are we looking for? The rate law expression, we're looking for the rate constant, and we're looking for the overall reaction order. We are going to see one little twist here, so hang on with me to see that one little twist. Okay, so rate law expression always starts out the same way. Rate is equal to K times initial concentration of one of our reactants times the initial concentration of the other reactant. If you had 3 reactants, you'd have to include all 3. Okay, now to finish off that rate law expression, we have to figure out the exponents that will go on the A and the B. And so let's take a look at what happens with, if we want to keep A constant, what's happening with B, and what does that affect on the rate. So find 2 trials where A is constant. It looks like trials 1 and trials 3, A is constant. So what's happening with B in those 3 trials? I see here that we're tripling. So this one's a little different here, that our base number is not going to be 2, it's going to be 3, because we're tripling the concentration of B. What is therefore the effect on the rate as we go from the smaller concentration of B to the larger concentration of B? We see here that the rate does not change. The rate is the same. Okay, so when that happens, when the rate does not change, what we have here is that the rate is going to just be 1. And therefore, what exponent do we need in order to take this tripling and bring it back to 1? Well, that means the exponent has to be 0, because anything raised to the 0th power is 1. So that means we're going to put an exponent of 0 on B, which really means that's going to be multiplied by 1. So B is actually going to just drop out of this rate law expression altogether. All right, so now let's take a look where B is constant. What happens to A? Okay, so let's go back to our data table. Where B is constant, we see these 2 trials right here. Okay, and from trial 3 up to trial 2, we see that there is a tripling. Okay, so where A is going to triple, what is the resulting effect from those same trials, from trial 3 up to trial 2? What's happening? We see that that rate of formation from 3.0 times 10 to the negative 4 up to 9.0 times 10 to the negative 4, that is a tripling. Okay, so this was a tripling, this was a tripling. Okay, so what we see here is if the tripling of the reactant causes a tripling in the rate, then that means the reaction order has to be to the 1st power. Okay, so how do we write this rate law expression? It is just like this. The rate is equal to the rate constant times the concentration of A. If we skip to part C, the overall reaction order, right, is overall, if this is a 1st order. Not much to it, there's only that one exponent. All right, let's jump back to part B. What is the rate constant? This is where we rearrange the equation. K is equal to the rate over the concentration of A to the 1st power. So plugging in the information from trial 1, we get 3.0 times 10 to the negative 4, negative 4, and that is the unit of moles per liter per minute. The concentration of A was 0.10, and that is moles per liter. If we see here that moles cancel and liters cancel, now we're going to see a very different kind of a unit here. We're going to see that the unit is just 1 over minutes. Okay, And if we do the math, our calculator is going to tell us it's 0.0030, right? So there's our rate law constant. You could also express it as 0.0030 minutes to the -1 power. Okay, so there we go. There you have it, rate law expressions, a couple different twists and turns throughout. And thanks for your patience. I know it's a long set of video lectures, but it covers 2 days in the classroom. So, all right, thanks for listening.